Bonjour à tous. Okay, so this is a cheat sheet summary on the topic of atomic structure. If you would like a copy of this cheat sheet, you can get one at the coffee shop, and also consider signing up for a membership with us. And yeah, okay, let's go into the topic right now. So atomic structure is one of the first few topics that you will learn, and I classify it under the fundamental toolkit of chemistry, and so we sell the cheat sheets as a set of 4 topics: atomic structure, chemical bonding, gaseous state, as well as stoichiometry. So feel free to get one on the website. So atomic structure, I will not go through the subatomic particles, right? Because you kind of already know this, and you can read this on your own, right? Just know that the charge values and the mass values here are not actual; they are relative values. Okay. So one of the few popular question types that like to come out is the deflection of charges. So the deflection of charges tells you about the angle of deflection of a particular charge in an electric field. So this angle is directly proportional to a charge. The electric field is uniform, so something that has a larger charge will be attracted to that side of the electric field more than something that has lower charge. So say like Fe3 plus would have a larger angle as compared to Fe2 plus. This angle of deflection is also inversely proportional to the mass. So think of it as like you're using a fan to like blow a ping pong ball versus a bowling ball. So obviously the ping pong ball is going to fly, right? So think of it, okay, this is just an analogy, right? So think of it that way. So something that is lighter will fly more than something that is heavier. So you put all of this together and you get this relationship. Theta is proportional to charge over mass. So opposites attract. So the negative charge will fly towards the direction of the positive plate, and the positive charge will fly in the direction of the negative plate. So something that you need to take note of as well is where this angle is. So the angle is actually according to the horizontal, right? So if it flies this way, the angle is actually this. That's something that most people draw wrongly, but okay. So an example I give you is over here, electrons are deflected much more than protons because electrons are 1,836 times lighter than protons. Okay, so now we move on to electronic configuration, which is something that you should already have learned before. Just that now we introduce you a different way of naming, of telling us electronic configuration. So this is known as the Spdf notation, and it follows 3 main rules. The first is the alpha principle, which tells us that electrons must be filled in the order of increasing energy. So there are a few ways that you can remember this. Most people learn it by the diagonal arrow method, right? So the diagram that kind of looks something like that. So I don't like to remember that diagram. I prefer to just use the periodic table because periodic table tells you everything, right? And the periodic table is given to you in the exam. Okay, so if you just look at periodic table, it tells you what you want. So if say I want to look for an atom that is in this position over here, or what I call it, right? So you just follow a periodic table. 1s, okay, so 1s, 2, 2s, 2, and 2p, 1, 2, 3. That's it, right? Even if you were to get a transition metal somewhere over here, you just follow a periodic table, blah, 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 3p6, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d, 1, 2, 3, right? And you just write them in numerical order. Okay, so next rule is Pauli exclusion principle, which tells us that each orbital can only hold a maximum of 2 electrons with opposite spins. So you need to draw it this way, 1 up, 1 down. And then Hund's rule tells us that each orbital must be singly occupied before pairing up. So this means that if you have something like 2p2, you must draw it this way. And only when you have something like 2p4, 2p5, 2p6, then you start to 2p3 and then 2p4, right? Then you can start to pair them up. Something I forgot to mention as well is about filling and removing the 4s first, right? So based on this periodic table method, you can see that you fill the 4s first and then the 3d. Why is this so? It's because the 3D subshell is actually at a higher energy level than the 4s when it is empty. And once it starts to get filled, it goes lower than the 4s. Why? Because 3 is smaller than 4, right? So once 3 is filled, it becomes smaller than 4. Okay, energetically speaking. Yes. So some exceptions to this electronic configuration based on these rules here is chromium and copper. So if you look at the periodic table, chromium is actually here, and copper is actually here. So if you were to use the periodic table method that I mentioned earlier, you would actually call chromium as 3d4 and 4s2, and copper as 3d9 and 4s2. So why did we change it, right? So what you observe is actually one of the 4s electrons goes into the 3d subshell. So why is this so? Because as an analogy, if you look at 3d, 1, 2, 3, 4, 5, this, all right, you have 5 boxes, right? So if it's just 3d4, right? Okay, if it's just 3d4, all of them are not parallel. Okay, so you bring one from the 4s down to a lower energy to get this balanced structure here, balanced configuration. Similarly for copper, right, you just go from 3d9 to 3d10. Okay, so in all cases for electronic configuration, we always want to achieve a more stable electronic configuration. More stable means lower energy. Okay, so if we can achieve such a stability by moving the electrons, of course you can't anyhow move the electrons. Okay, so these are 2 exceptions in your syllabus that you need to remember. So the next part that we're moving on to is about orbitals and subshells, which is quite simple because it's just drawing, right? So principal quantum shell number is these big numbers here, 1, 2, 3, 4, 5, 6, 7, and they tell us the main energy level, relative size, and the distance from the nucleus. So a larger shell number relates to a higher energy level and a larger size and a greater distance from the nucleus. Next is the subshell. Subshell tells us the shape of the orbitals. In your syllabus, there's only SPDF, and you only need to know the shapes of S, P, and D. So S is spherical in shape, P is a dumbbell shape, and D is a clover leaf shape. Okay, that's all you need to know. An orbital is basically the region where there's 90% chance of finding the electron. This is different from what you drew last time, that planetary diagram, circles, and then it must be north, south, east, west, or whatever way that you learned it. Because of quantum mechanics, we realize that electrons are not actually in a fixed place, but they are in a region of space. Okay, so S is very simple to draw. It's just a circle, right? Because this is your paper is 2D, right? So you can draw a 3D diagram. Next is P. These subscripts here, Px, Py, Pz. So this X, Y, Z tells you which axis the lobes lie on. The lobes lie on, right? So Px means that the lobes lie on the x-axis, Y means that it lies on the y-axis, and Z means it lies on the z-axis. Of course, I'm not telling you to draw it this way. You can always reorientate it as long as if it's Px, your lobes lie on the x-axis. Okay. Now, next is the d orbitals. So d orbitals have clover leaf shape, and if it's like something like, so there are 2 main types, right? So one is x, y, x, z, y, z. So that's the first type. If you see a product of 2 of them, this tells you that the lobes lie between those axes. Okay, so as you can see, I drew the same diagram for all 3 of them. Why? Because you use the axis to your advantage. Okay, so if you see, I draw the same thing, but I change the axis. The next one is the squares. When you see a square, it tells you that the lobes lie on that axis itself. Okay, so x squared minus y squared means that the lobes lie on the x and the y axis. If z squared, it lies only on the z axis. And this one is a bit special. It has these 2 rings here. Okay, so don't forget to draw those. Next, we look at the main bulk of this topic, which is periodic trends. So 2 main concepts you need to know is nuclear charge and shielding effect. Nuclear charge relates to the attractive force of the positively charged nucleus for the valence electron. So this is an attractive force, and it depends on the number of protons that the atom has, because larger number of protons, more positively charged, so stronger attractive force. Shielding effect, why is it called shield, right? The nucleus is in the center, and then the valence electron is all the way outside. So the shield is the inner shell electrons, right? So all the inner shell electrons. So the shielding effect depends on the number of inner shell electrons. So you take attractive force minus repulsive force, you get a net attractive force, and this is the effective nuclear charge. So two properties can be derived from this. One is the ionization energy, which is the amount of energy required to remove the valence electron. So if you think about it, if you have a higher effective nuclear charge, this means that you have a larger net attractive force. And to pull the electron away from this attractive force, you need more energy. Okay, and if you have a higher net attractive force, your electron is pulled closer to the nucleus, right? So your radius is smaller. So you can see that higher effective nuclear charge means larger ionization energy and smaller radius. So ionization energy has an inverse relation to the radius. So let's look at three main things that they like to test. First is across the period. So across the period, the number of protons naturally increase, right? So the nuclear charge increases. But the electrons are all added to the same subshell, you see, right? If it's 2p, right, you got 2p1, 2p2, 3. It's all in the same subshell, right? So no difference in the shielding effect. So the effective nuclear charge naturally increases. So the atomic radius will decrease. Now, why is there this strange diagram for the ionization energy? If you think about it, shouldn't it just be like one straight line? Okay, that's not the case. Okay, so for ionization energy, at this point here, from 2p1, from 2s2 to 2p1, you now go into 2p, which is a high energy state, right? And it's further away from the nucleus. Further away means less energy required. Therefore, there is that drop. Next drop occurs at the point from 2p3 to 2p4. Why? Because from 2p3 to 2p4, you have this paired electron. When two like charges together, there'll be internal repulsion, right? So this is called inter-electron repulsion. This inter-electron repulsion results in a decrease in the net attractive force required. So less energy is required to remove the electron. That's where the next drop occurs. Okay, next we look at across the transition metals. So you must be thinking transition metals also another period. So what's the difference? So the difference is if you look back at the periodic table, you fill the 4s first, then you fill the 3d, right? So 3 is more than 4. So 3d is an inner subshell. So when you now add to the inner subshell, you contribute to the shielding effect. So now that you have contribution to the shielding effect, it increases. Therefore, this nullifies your nuclear charge to a certain extent, right? So your effective nuclear charge doesn't change much. It doesn't change much, but it does change. So the atomic radius will decrease by a bit, and the ionization energy will increase by a bit. Okay. Next, we look at down the group. Down the group is the easiest because the number of shells increase, right? Down the group, see, you go 1, 2, 3, 4, 5, 6, 7, simplest. So when that increases, the valence electron is further away from the nucleus. When it's further away from the nucleus, by inverse, so the radius is smaller. Radius is larger, right? Further away from the nucleus, radius is larger. So from this, right, inverse relationship, the ionization energy is naturally smaller, larger radius, smaller ionization energy. So if you forget all of these, right, there's one way you can cheat in the exam. You just look at your data booklet. That's not cheating, right? Because you're given the data booklet. So if you look at the data booklet, page 42 and 43, they actually tell you the list of radius. This ionization energy. It tells you the ionization energy values, right? So you can draw some trend from these. Next is if you look at page 51 and 52, it tells you the atomic radius and ionic radius. And from this, you can draw your own trend, right? So that's one way you can use the data booklet to your advantage. So that's all for this content summary. If you would like a copy of this, again, you can always get it at the coffee shop. Link is in the description. And yeah, see you around for next few content videos. If you like this, consider supporting the coffee shop and consider signing up as a member as well to get your questions answered. Bye-bye.